Başlayalım, nasıl yapalım?
Başlayalım.
Şimdi başkan konuşman var mı? Bir şey yok zaten de.
Başkan. Buyurun hocam.
Siz var ya öyle.
Güzel düşünüyoruz.
Herkese tekrar hoş geldin diyoruz. İbrahim tanıyorsunuz zaten, bir yıldır sizin ikisini kolaylardan dolayı gelemiyordu. Zaten bir yıldır bitirmiştik aşağı yukarı. Şimdi gelmek nasip oldu. Konusunda zaten bir tane ilerleme de olsa Murat hocamız var, Altay'da geliştirme komitesinde. Önden bir sorunuz yoksa başlasın. Soru cevabı isterseniz en son yapalım veyahut da arada aklınıza bir şey gelirse bir şey yapalım. İbrahim, you can start.
Thank you very much.
You can mention about yourself first of all.
Okay,
İbrahim Türkçe anlat ya kendini.
benim adım benim adım İbrahim. Ben Palestinliyim. Çok az Türkçe konuşabilirim. Ve ama biraz anlayabilirim. Ama konuşmak için biraz zor olabilir. Evet, teşekkürler. Doğru mu?
Good, that's a very good.
Thank you very much. Welcome. Actually, good afternoon to everyone. Thank you for your coming. Welcome to our PhD Thesis Defense entitled with Enhanced Control Structure for a Grid-Connected Photovoltaic System under different operating conditions, supervised by Dr. Ahmed Tekki and the committee member Dr. Tayo and Dr. also Wara, Dr. Özgür Çelik, and also Dr. Hassan Zor. Dr. Uzan, and sometimes like this letter I have problems with it. So Dr. Uzan, I think. Thank you very much. Thank you. The presentation is subdivided into 8 parts, which include introduction about the issue, the problem formulation, which include also the objectives and the contribution of the thesis, also the overview of the grid-connected photovoltaic systems, along with the inter-harmonies from the grid-connected systems, and we have the proposed of course, integration technique of the inter-harmonics and the proposed mathematical modeling of inter-harmonics. Then we move to this second part of the thesis, which is the enhanced control structure of the grid-connected photovoltaic system under multiplication profiles. Finally, we have conclusions and recommendations. I will start this presentation like that. Everyone nowadays is competing to install more electrical, more photovoltaic systems worldwide. So as we can see, the increase in photovoltaic system is exponentially. This is 2023. It's very new. But in the opposite side, we can see the reason for this is the decrease exponentially in the price. So the countries are competing to increase the capacity of the total installed photovoltaic systems. For example, Turkey is coming in the 14th place worldwide, which is a good number, 3.2%. We have Europe 60%, and some countries like Denmark, they are targeting 100% of PV usage by 2035. So what is the impact of this increase, the huge and massive increase in the residential and in the also the big companies? We have technical and economical issues. From the technical point of view, we have related issues related to the inverter itself. We have the cost of energy of the photovoltaic systems, and we have the grid integration issues. The grid integration issues is coming because the photovoltaic energy is depending on weather. So this is problematic. The second thing is like for the bulk systems, this will cause load fluctuation and also stress the voltage at the point of common coupling in the case of active power injection. So this will actually affect the power quality of the grid mainly. So more investigations should be carried out for this huge and massive amount of grid integration, even from the residential, like us, and the university, and the homes, and also for the bulk, the big companies. Why? Because the direct connection here at the point of common coupling is actually impacted the grid in a negative way. Why? Because we have the inverter in here, and it recently has been reported as a source of inter-harmonics and harmonics injected to the grid. So this will affect the customers here, and also will affect this customer because the inter-harmonics also will come back from the other here. So the power quality issues usually they are classified into 3 parts. we have frequency events, voltage events, and waveform events. We are working in this thesis on one of the waveform events happening in the steady states called interharmonics, and which are defined as a non-integer multiple of the fundamental component in the voltage or the current. So we will talk about this later, but they are not 50, they are not 100, they are not 150. They are like numbers like 65 Hertz, 66 Hertz, and this is very challenging in the detection process, as we will explain. So what is the idea? What is happening in the VB inverters? Actually, the problem is coming for searching of the maximum power extraction from the photovoltaic inverter. During this search, the DC link will be affected and interharmonics will be generated and will be injected to the grid. So how they look like? What is interharmonics? It's something like this. This is the frequency spectrum. They are spikes. We have as this is 150. It's not 150 the third harmonic. So this is 85. So they are sub-integer multiples of the fundamental frequency and not integer multiples of it. So how they are coming? This is, for example, the injected current to the grid under low power breaking condition, and this is under the full power breaking condition. Both of them, they have the same, and this is important, the same frequency and peaks. Because the literature, there is a contradiction in the literature. Me and Dr. Oscar, before we had a problem. There is one published paper. They are even the same group research. They are contradicting each other. They are saying in one paper like there is a difference, and the other paper they are saying there is no difference. But all the work that we did, it's the same. Like the low power and the full power breaking conditions, they are indicating the same frequency. And this is actually problematic because someone will think at the full power, I will have no interharmonics. It's a pure sinusoid. No, this is wrong. We have, and this is one of the important points why we should study interharmonics, because it's happening either ways. So what will happen actually? What interharmonics do? Flickering, overloading. Of course, we know this. Tripping protection devices. Also, sometimes impose thermal stress. It's spikes with sometimes high amplitudes. This is from the point of technical point of view. But from money-wise, there is like some studies done in Spain, for example. They studied the interharmonics and harmonics in their grid. This is the holy grid of Spain, the low voltage, medium voltage, high voltage. How much they lose because of harmonics and interharmonics. The total amount back in the days, it was 36.6 million. Nowadays, with the capital price of the kilowatt, this is the updated one, it's almost 181 million euro per year because of this, but of course the whole Spain. But Spain network is tired, like it's exhausted. It's 4% total harmonic distortion. Quebec, Canada is much better. Like Canada is bigger than Spain. The numbers here is giving like a little bit better money-wise numbers. But there is, for example, this is a very interesting study, 2018 in university campus in Ghana. They measured the total harmonic distortion in the university. They found to be 60.4%, the students at the substation. So they did some installations to decrease this number to 8%. They are claiming that they are saving 13% every month out of the bill because of this. And they are claiming 6 years way back out of the installed or the modified system. So it's worth mentioning that if we can do this, if we have 1%, 2%, or 3% of reduction in the bill money-wise, we can do it, and we can, from the money point of view. Someone maybe asked, for example, a company guy or someone. So what are the objectives of the thesis? Of course, the literature review. We should look into the previous work. Also, what is to investigate the mechanism of the interharmonic generation, how it's regulated in the system, and how it's injected to the grid. Also to investigate the maximum power point tracking compression, because as we mentioned before, it will be a source of interharmonics, and also enhance the concept structure to mitigate the interharmonics by modifying the control structure directly or by modifying the maximum power point tracking algorithm. Also, we can investigate the mathematics behind interharmonics. For example, mathematical representation of the interharmonics in the signal, how we can do this, we reduce it. Also, the simulation cases, conduct extensive simulation cases because those kind of studies they need a lot of data just to look for the spectrum we will see in the results section under different operating conditions. Also, for the developed and modified maximum power point tracking algorithms, and compare, the most important thing is to compare them and to find which one is giving the best result for the interharmonics. Also with the ones available in the literature, like also we will have to compare with the maximum power point tracking algorithms also available in the literature. Also, to have to investigate the performance under dynamic grid support, let's say under low voltage driving through situation and reactive power injection, and the effects of some parameters like this, the effect of low voltage driving through and the variation, for example, of a grid frequency, the some faults like voltage sag or swell on our proposed maximum power point tracking algorithm, and also on the interharmonic generation. What is the relation for those issues? The main contributions of this thesis, as I mentioned before, first of all, confirming the power independence for the interharmonics. They are changing between low power and high power. By the way, we just published a paper and we indicated that there is no dependency, for example. I think this is because even while I'm updating myself for this presentation, the recent literature, there is a lot of people copying from each other. Like someone saying there is dependency, the other one saying there is no dependency, and this is misleading. Also proposed the contribution to the mathematical model development of the maximum power control algorithm, which modifies the control structure. But we will propose do some mathematics to the maximum power point tracking algorithm parameters between two quotations, modify them by a mathematical function to modify the operation of the system. Also propose a multiplication technique of interharmonics based on the modification of the maximum power point tracking parameters. We will see in a moment that they have a huge effect on interharmonics. Also trying to develop a mathematical expressions expressing the DC link voltage, coupling the photovoltaic and the grid connection, mathematical expressions in terms of the parameters of the maximum power point tracking algorithm. This will be an important point. The last, but not the least, to verify also the effect of different operating conditions, because as the title of the thesis indicating, we have the full power, the low power, we have a lot of sensitivity analysis like the variation of the DC link, blah blah, and those kind of stuff. We have also a comparison between the proposed maximum power point tracking algorithms method and the existing one in the literature, and also we have to investigate the interharmonic generating characteristic under dynamic grid support, or let's say the low voltage driving capability of the system. Finally, this will contribute to the research by having some kind of articles. The flowchart of the thesis we explained before by the objectives and also the contribution. This is like we have 5 basic: the literature review, the fundamentals, the design and decide everything, and propose the mathematics and propose the methods here. Then we have the what's called the active and the active power support, and final conclusions. Let's start with the related work. Actually, it's very few number of papers about this topic. The first paper, it was in 2016, about indicating that the issue of interharmonics and the photovoltaic inverter is a source of power quality issues. Let's say interharmonics between two positions. Then we have a guy called Arya. He just took the lead for everything after that. And this is what I'm talking about. There is here some kind of contradiction. There is a conference paper he has published, and there is issue with the results, the frequency between the high power and the low power. But the same guys, they published journal papers after that, and they are indicating that the power is the same. But there was a gap, like 2017 and 2018 and 2019, like there is 2 years or 1 year and a half between them. So as we can see, all of them, they are in the range of residential power, like 3 kilowatt to 4.6 kilowatt. So our system 3.7 is the one that we are simulating. The topology is LCL filter, of course, DR control. This is the preferred one for analyzing the interharmonics, because actually the VR controller itself is suppressing harmonics and interharmonics. We just combine the literature, the specific topics. We can go to each one, but those are the most important ones. The economics from generated from the grid connected photovoltaic system, the ones that we mentioned before, and the impact of grid connected photovoltaic system on market quality is really important. Those are the mathematical modeling and also the relation to the total harmonic distortion. Also, this one is the harmonics. The principle of harmonics in power system as a whole. It's good to see how the other techniques used in the other systems, like wind turbine, for example. We can maybe apply this technique to the photovoltaic system, because, for example, the wind turbine is a changing variable, like the wind, like the sun. So those techniques maybe they are interchangeable. Regarding interharmonics and control, we have the linear and the non-linear control. We are working here, the BR controller, the resonant and proportional resonant controller. It should be controlled in stationary reference frame because of the sinusoidal different signals. We can, for example, I saw this, like the BI controller, which we will be using for the DC link, the outer loop. It should like deal with constants, like EQ, or let's say bar transformation. But for the stationary, this is important for designing the controller in our systems. For the stationary signals, we have to use something. The control itself is stationary, which is the PR controller. As I mentioned before, this is the control system. It consists of the outer loop, the DC control loop, the BI controller. We have the VLL for grid synchronization. Of course, we have low pass filter because we have the DC link contains the coupling, it contains second double frequency of the grid, so we have to filter it. So this is low pass filter. And we have the inner control loop, the current control loop, the VR controller, and also, of course, the multi-modulation signals to the inverter. So how the interharmonic generated? As we mentioned before, we know that the photovoltaic system, we have the DC link. So if I'm measuring the voltage and I have a reference, so the minus will be what the error. So this error is here. If I'm taking this error and do the power frequency spectrum for this error, I will get some kind of interharmonics. We will talk about this later. This interharmonics is coming here and will be going all the way here to the grid current and will be synchronized. This process is regulation. I'm multiplied with sine theta. So sine theta multiplied by a magnitude in here, it will be shifted left and right. So all the peaks in here coming from the DC link will be shifted by the grid frequency. We will see this in a moment for the mathematics development of the interharmonics, and then it will be injected to the grid. So let's say for this model, we can conclude that it's the DC link perturbation, the source of interharmonics. For the other control system, for example, if we would like to develop the BQ control, the reactive power control, as we can see, the same principles applies. This is the DC link here, and we have here the B and Q reference. We just leave the Q reference, we will return back in the same system. But just we used the BQ single phase instantaneous power theory to control the system. There is additional component here is contributing to the harmonics, which is the power oscillation in this thing. This is a new it's a contribution to this thesis and to those systems, because this control structure I can just remove this. This is like a stabilization to the system. It's not required. So this system will work actually without the outer loop. But it's like the concept of feed forward. It's like stabilizing the system by the other BI controller. So the main source will be from the oscillation of the power of the maximum power point tracking, because the maximum power point tracking here is giving power source. So the same concept, the current is coming here, injected to the grid current and coming back as this is the single phase BQ theory is used, developed for the out of the single phase. Of course, employing the maximum power point tracking algorithms, we have a lot of algorithms, I could mention something that we have offline and online. So the thing that we need, because we need continuous monitoring, maybe online is coming as a feasible solution. And we have another thing which is important. We have to search for the well-known and the most used maximum forward checking algorithm in the market. Because if I am a customer, we are studying internal mix of the customers, the residential, for example, residential inverters. So I will have 5 kilowatt, for example, inverter at home. It will be cheap, maybe from China, implemented the vertical and observed or incremental conductance or those. So from a search that I did, they are mentioning that most of the used, they are the maximum power point checking algorithms, they are the well-known, the conventional ones, the vertical and observed incremental conductance. Even some use the constant voltage with a small PV cell just to get to update the constants of the maximum power. So we are interested in vertical and observed incremental conductance, constant voltage, and artificial developed artificial neural network model trained by the data that we have from the MATLAB and also available to the comparison. The interharmonics, this is the second section that we have. We are preparing the system to be simulated. This is the power circuit and this is the control circuit that we have. This is the MATLAB model of the system. We have the frequency signature generated. Actually, we used to be we use we know the time shift, the time delay T by 4 to produce the alpha beta. And also we use the second order generalized integral as which is robust and can resist the interharmonics. This is the power topology. We have the inverter control. The controller is discrete and it's a digital DI controller. We have the efficiency calculation in here. We have the maximum power point checking algorithms, those are the developed algorithms. And we have here also the PLL. We have two PLL inside. We have the, as we mentioned, second order, and also the time shift for maybe the camera filters. Finally, we have the pulse mix with population. The parameters of the system, the most important thing is we have the power in here. The design of the parameters of the LCL filter, it's well known. And also we have the sampling rate, it's very important, the sampling rate of the maximum power point checking algorithm. We will use it initially as 20 here, and step size of 5. Those parameters will be changing with time with us. First of all, we will start by using constant voltage maximum power point checking algorithm. As we can see, the current is very clean. Almost we have zero error in the DC link, the BI, there is nothing there. There is no perturbation, there is no error, and the spectra is very clean. It's 10 to the minus 3. It's almost zero. For the operation under, for example, vertical and observed control algorithm, as we can see, this is the full load operation. This is the no load or the low load and power operating condition under 5% actually of the full power. As we can see, this is the DC perturbation. We have the grid current, we have the DC error. This thing is 5 volt, which is equal to the 5 volt of the step size. Because if I'm making wrong with the reference, it will be something minus something will be 5, which is the step size in here. And this will confirm the accuracy in the DC link, and you can follow it. This is the current injected under the low power operating conditions. As we can see, the perturbations in the DC link from the vertical and observed, we should study if this perturbation is the source of the interharmonics. So this perturbation, as we can see, for example, let's count. I'm moving like this. This is, I change status 1, 2, 3, 4. So to complete one cycle and start again, I need 4. So this number I needed so much for the next study. This is the number of how much the DC system is, the VDC is changing itself. And we know that this is the sampling time of the maximum power point checking algorithm. And this is the fundamental period. It's T0. So T0 is equal to 4 times the sampling time of the maximum power point checking algorithm. For example, this is the frequency response of this, the decelerating curve. If we take the frequency response in here, we will see 5 Hz, 15 Hz, 25 Hz, those numbers. So if we are trying to understand those numbers, I didn't see, this is by the way, those equations are related to this thesis. They are developed by this thesis. They are not from the literature. If we are trying, for example, to calculate the separation in the decelerating, this is the decelerating frequency response. For example, if we take the maximum decelerating frequency, we remember it's a 20. So 20 over the number of changing the DC voltage, how much it was 4. So 20 over 4, it's 5. So we will get 5, the first 5. So if we multiply this equation with integer number, odd number, like 1, 3, 4, I did this by trial and error, and it applies to all the other methods. So let's try 3. 3 multiplied by 20 is 60 over 4. We should get 15. I don't know how, but we should, let's try it. It's 20 multiplied by 3, 60 over 4. It should be 15. It is 15. So I did like a long tables. I'm not including them in the thesis, but I did long tables to compare the results and to see what is happening. So this is the equation I called it's F and DC, which is the separation in the DC link. So if we would like to see what is happening, like this equation, it was 515. Let's like focus here. Let's from the after the fundamental frequency, we have 55. So the 55, how to get, for example, that number? This is the grid current. Like after doing the modulation, the grid synchronization, we thought that it will be shifted. So this number is actually the equation that we have plus minus the grid frequency. So for this number, we have 5 Hz plus or minus 50, it will be 55. So all the frequency, it's actually the process of synchronization is frequency shifting in the frequency domain. So all the grid frequencies, the interharmonics that we are seeing is shifted because of the synchronization process. As we can see, it's 5 correspond to this one. This is the final form of those interharmonics. So we can see that, okay, we have 20 and it's affecting 20 Hz sampling rate with the maximum, and we have 5 volt which is affecting. So what is the effect of sampling rate and the determination step size on the maximum Bell channel algorithm? We know that both of them, they have special effects. For example, the step size, if we are increasing the step size, it will be problematic for the if it is like a small step size and high sampling rate, it will be the best. I can enhance the efficiency and I can also enhance the tracking speed. But it will come on the cost of interharmonics. We will see this condition is increasing the interharmonics in the system. For example, we have a step size of 2 volts, 6 volts, and 10 volts. As we can see, this is the injected current under low power operating condition. As we can see, the peaks of the decelerating voltage is increasing with increasing the step size. This is logical. But this is the most important thing, which is the frequency simulation of every decelerating voltage that we are getting. As we can see, the same frequencies, this is important, 55, 55, 65, 65. So the effect of sampling step size is not affecting the shifting process in the grid current. It's only affecting the peaks of the interharmonics. This is an important concept. This, for example, we can use the same equation and we can get, by the way, it's the same frequencies, so no need for the calculation under this case. To compare the interharmonics generation, as we can see, as we are increasing the step size, the interharmonics are increasing. So this is an important point. For the second parameter, which is the sampling rate, as we mentioned, increasing the sampling rate will increase the efficiency, of course. And this is what it looks if we are changing the sampling rate. Actually, we are compressing, like if we're using 32, for example, very high, 32. It will like do a lot of repetition in one cycle. So 16, we used 3 sampling rates. We used 8, 16, 32. It's reversed. 32, that's 8, 16, 32. The effect on the frequency spectrum is really different under this case. As we can see, the numbers, they are like, we don't know, 102, 94. It's not like 65, 55, something that we can understand. However, the equations that we have, they also can predict. Let's say, for example, any number that we need, I don't know, all of those, but what I mean, the peaks, those equations, they cannot, for a reason, they cannot predict the harmonics in between, the small ones. I noticed this, only the big peaks. For example, the 58, this is 32, so if we do the math, 32 multiplied 52 over 4, how much it will be? It's 32 over 4, it's 8. Oh, sure, it should be 8. 50 probably great, 50 plus 8 is 58. I just wanted to confirm. I don't know, I did this before a while and using Excel, so I don't remember. But those equations applied to the variation. So someone could think, I can use those equations for neural network. I can design a detection tool. I can use it as a signature. It's a good idea in the future way, but I wanted to mention it in here for our future studies. So, as we mentioned, of course, increasing the sampling rate will increase the interharmonics, dBs, which is very important concept. So, as we explored until this time, we know that the grid photovoltaic, recurrent photovoltaic system, they are a source of interharmonics, one way or another. So we need to think about a single, let's say cheap, without the hardware changing or anything that we can improvise from the literature or from ourselves. We found that in the literature we found two ideas. The first idea is like sometimes they are changing the Watt's modulation in a random way to reduce harmonics. This concept is used in the Watt's modulation. Also, there is like in the literature, there is someone who used this concept with the sampling frequency. I don't know why he didn't use it. He didn't analyze the step size and he didn't use a combination. In our research, I see that the step size effect is dominant, is more than the sampling rate. I don't know why they didn't contribute to the research and do the, even we have maybe 10 or 15 papers only about the interharmonics. So the idea of proposing the technique was like this. Like we will think like, okay, we have the best optimal values. For example, sampling rate. The optimal values is between 1 and 20. This is from literature. 1 Hz to 20 Hz. For the step size as well, we will put like higher limit and lower limit. Higher limit for the step size and higher limit for the voltage perturbation. And we will change it randomly, for example. We don't know what is the current status of any of those two variables. Let's say V1, it will be from 2 to 5 volts, and the frequency will be from 8 to 20, let's say, or from 1 to 20. We can pick any of those. And we will change. For example, we can create a function in MATLAB, and it's a random number. For example, I'm letting MATLAB to give me a random number between 0 and 1. The algorithm will decide if this number is less than half, it will choose this rate. If the number is more than half, it will choose the other rates. So it will be fluctuating in this way. So we can get the step size, the random step size, and the random sampling rate. There is a mistake. This is sampling time. So in the MATLAB it's divided. So this one is 20. So the numbers and the step size from 2 to 5. Applying the same system to the last blind hour method. What happened with the results with the interharmonics? As we can see, this is we actually divided. We applied the system in 3 steps. Only we did a random step size. Only random step size. We did only random sampling frequency, and we made the what's called hybrid random, which combining both of them and to see what is the effect. So the result of changing the step size, it will be like this. You can see the
the steering is not good. Changing the frequency, we can see it's sometimes small, sometimes big. So this is a hybrid. It's mixed. It's changing the step size over the sampling rate, doing it in a realistic way. So what happened with this case? If we would like to compare the three methods, for example, if this is the conventional data observed, we would like to change the sampling rate alone, we will get the frequency split by the harmonics we saw the green. If we are changing the step size and the sampling rate, sorry, we are getting the green. The green is the lowest one. We have the fixed, sorry, this is not the conventional, this is the fixed step size, which is the conventional, of course. There is another figure. Okay, I was just mistaken. The conventional vertical observed, this is correct, compared with the random sampling rates and this random step size and sampling rate. This is the proposed algorithm, and this is the literature algorithm. There is something like this in the literature. So the green, we have improvement of over 26% over the literature, the one, the 2018. So this is important. And we have the conventional vertical observed. If we comparing all the methods, as we can see, the vertical observed, variable step size, variable sampling rate, and also the hybrid. As we can see, the biggest one for interharmonics. For example, if we compare the normal one and we will see the maximum peak for the developed algorithm is 0.08, where in the conventional only a single peak, the highest peak is 0.26 amps. Of course, this is summing all those components multiplied by the grid voltage, so it will be huge for the watts. The algorithm is like decreased the peaks 3 times. This is why it's almost 27% decrease in the system performance. Efficiency calculation, I will go very fast for this section. It's important, but the method is very efficient. We calculated the efficiency as the total extracted power over the available power over 9 cases. Those 9 cases, we have, this is the proposed algorithm, and it's the least harmonics, and the efficiency is 97.3. It's a little bit, the efficiency is a little bit lower than the optimal condition, which is 220. But this condition is like very, very high in the harmonics. And if you would like to see the difference, there is no difference. It's almost 0.0, it's like 1%, 1.5%. But in the other slides, we will see that this method improved the efficiency in a lot of cases for over than 25%. Like because of reducing the total harmonic distortion in the system. We will see it in the active and the active core section. So the leading one in here is the hybrid random algorithm. Also, we have some methods compared to the literature, 2 methods compared to the literature. But here we have like 3 stars on this one and this one, this one and this one. So, which is the conventional, of course, and the sampling rate, the variable sampling rate. Those are the efficiency. For the efficiency calculation, we use trapezoidal. It's a realistic data. I found it on the internet. I managed to stress the data for 10 seconds. Then I ran the simulation. It took a lot of time, but it's given a smooth and very realistic starting and getting down solar irradiance. So this is our proposed method. It's the 97.3, and the best and the lowest. This is the lowest, and this is the best case, 97.5 and 97.3. But this method is maintaining the total harmonic distortion minimized, and also there is no interharmonics. So it's a trade-off again, but it's preferred over the literature, over the other methods. The second phase of this work, we are working here for the mathematical modeling of we are started the mathematical modeling and the sensitivity analysis of the system. I would like I would like to introduce the idea of this DC link voltage. If we can mimic the behavior of this DC link, like I can construct this signal using Fourier series, for example. Imagine that we can write it like this way, and we can do Fourier series for the signal itself. Find the constants S0, Pn, An. Those constants I can construct the same signal again. Like I can construct it out of Fourier series. If I can design a closed loop system from VDCL to VDC out and apply this signal by Fourier series, I can, for each frequency component, see what is the response. It's a discrete system. So if we can do this, the DC link we can represent it as a step function, of course, and we can find the coefficients using Fourier series, S0, A, and Pn. For example, S0 will be the average, of course, so it will be VDC prime. Those coefficients, they are available in the literature, but they are different. So for our study, this is a new coefficients for the maximum point tracking algorithm. Then the parameters, Arias parameters, they are different. They are not the same. Even I try to draw Arias parameters, they are giving something, I don't know. So those also a contribution to this work, like a new parameters for the maximum point tracking algorithm. This is I calculated them by coincidence because I tried the factors and they didn't work, so I used MATLAB simple integration and I did the calculation also by my hand. Both they get the same answer, so we confirmed Dr. Özgür and Dr. Ahmed, they are the same. Even Dr. Ahmed, he just contributed a lot to this. We are very sure about the constants because we draw them, of course. This is the calculation of Pn. This is the Vn, and those are the factors alpha beta. So after this, we have now the VDC link. We have the closed form S0, Va, and Pn. So we can write the VDC link in one equation. We can go now and design the closed loop system. Okay, the closed loop system, which is from the VDC, the outer, the reference VDC, to the grid current. And in the feedback, we have the planet and the notch filter, or the low pass filter. The notch filter or the pass filter, they are the same. They are the same. And the DC link controller and the current controller, just setting the, I don't want to go through the transfer function, all of them, but they will know the control system and the grid control system. We can use the closed form of the closed loop transfer function. We need it because we need to see what is the response of the system, the total system. Imagine that we would like to calculate the grid current for each discrete value. So Ig of 1, for example, is equal to the response of that transfer function multiplied by the sign, which is the phase of the system. So if we would like to calculate all the current, it will be the summation from 1 to infinity. So this series will construct the DC link voltage again. So we can construct it again, and of course, this is a mathematical, a closed form mathematical solution for the grid current. This current, actually, it's the reference out of the VI controller. And this current will go and will be multiplied by the grid, the synchronization process. And any sign multiplied by sign, it will be modulated, left and right. The Fourier transform theory. So it will be like left and right. So here, Fg minus Fn, Fg plus minus. So this is the manipulation happening to the DC. Do you remember the peaks of the DC link shifted by Vg? So this is the mathematics behind it. This is how it goes. Those are the implementation of the system. This is from the reference VDC to the measured one, the closed loop, and also we have the from the VDC to the grid current, the one that we designed. This is the reference signal, the one constructed from the Fourier series, and this is the one measured. So somehow we are trying to mimic the system, what is going on with that system, we do Fourier transform of this signal to find the spectrum. Do you remember 5, 15? So the same numbers. So we use here 20 hertz of sampling frequency, and we get the same results always. This system needs more development of quantum mathematical model, but it's a good start, like to modeling the interharmonics. Now we are moving to the second part of this thesis, which is the BQ control. The BQ control, we need to investigate the inverter, the power mix, under both active and reactive power support and low voltage right through with other, with all compared with the other maximum point tracking algorithm. We just now we apply this to inverter and observe. We have the other methods that to modify the quantum structure for and to see and to compare them. What are the results among the conventional, the enhanced parameters. So the inverter, for this section, we know that the grid is a sort of abnormalities. For example, I'm living in the university. All the time I'm having voltage dip. And my PC, I don't have a battery, so sometimes maybe it will cause some issues. So voltage dip is very common for the. So what will happen in the new moment of voltage dip on the from the side of inverter? Does the perhaps increasing? Should we inject reactive power? While injecting the reactive power, how the interharmonics will interact? So all of those issues will be discussed in this section. For the operation of the voltage rally through, it's actually kind of dynamic grid support. We can't say exactly it's active and reactive power, but it's kind of a dynamic grid support. So during the appearance, for example, of a full voltage sag, the voltage is going down, the inverter is required to support a little bit of reactive power or to absorb. It depends. For example, in my opinion, most of the cases, imagine that we are living in a neighborhood, everyone is connecting inverter. So, and everyone is injecting power. So I will think that I have a lot of active power in the grid. I need inverter to absorb reactive power to reduce the voltage. I will accept that expect the point of common coupling to be overstressed by voltage. Maybe the inverter will not all the time supporting the reactive power. So during the low voltage rally through, this is the important point. If you are thinking about it, there is like, for example, a residential or a commercial building. It's rated power, it's supporting the rated power. If we would like to support the active power, sometimes reducing the peak generated with the active power is a good idea because to maintain the power factor. And that only is a good idea, but it's optional. There is like no specific codes for the residential, unfortunately, residential inverters. But it's good to know this thing. For the low voltage rally through, there is a code, it's different codes. This is one of them, of the codes. It decides like how much the voltage, when I will disconnect after 1 second, half a second. If the voltage sustain, like with this amount, the inverter will, of course, support reactive power, but up to some limits, 1 second, 1.5 seconds. Sometimes it's required to support reactive power for the whole period, but this is for low voltage rally through. The inverter will assist the grid to return back to its situation. So what we will do, we will apply the same concept to different algorithms. We have the inverter and observe, we discussed before. We have identified voltage, identified frequency, the hybrid. We have the incremental contactors. This is a new one. Actually, this is a contribution to our definition. I identified even the random application for the incremental conductance. So defining the incremental conductance is also a contribution to this thesis. And also finding the modified random of the incremental conductance. Also a contribution which is the neural network controller that compare. Of course, we will take a lot of data, but it gives the best result. Of course, there is no variation in the DCM. It's very, very sharp, very straight. Of course, we will compare them also for multi-emissions. Those will be compared to low voltage rally through DC link and frequency variation indicators. If we will start with the normal operation,
I will go very fast maybe in this section because we know the concept now. We know what is going on with the frequencies and GC-link, but those simulations we introduced the total harmonic distortion.
Ibrahim, just focus your contributions, especially neural network-based control. Okay.
Okay.
These are the traditional. You can.
This is sure. Okay, I will go very fast. It's only that I got all the results in a single slide after that. But this is the status information. I wanted to show the phase shift because there is here this controller is working active mouse support, so someone should see the phase. It's in phase and the cruising, and also the perturbation of the DC along with the value of the grid. By the way, all the design they are complying with the grid standards. The total harmonic distortion in this figure is very low, so it complies with the grid standard connection and etc. Of course, 2.4% for total harmonic distortion and the efficiency of 96.4, which complies 100% with the grid standards. So the proposed modified step size, those are, as we can see, the harmonic distortion is very high under the low power operating condition. And we will see maybe what will happen with the proposed method. It will be able at least to minimize the total harmonic distortion. So this is the modified step size. As we can see, those are the results. We know comparing the modified size with the original will be better. Comparing the frequency and the modified frequency and the conversion, it will be better. So those are the three results, and also with the modified both the hybrid frequency and step size. We are also the proposed algorithm. Those are the results of the proposed. As we can see, the DC-link voltage is changing in a different way. It's not because of the random sampling yet and the sampling step size. As we can see, comparing, if we remember, it was very noisy, the total harmonic distortion. Of course, we have some peaks, but it's settled somehow. And this is actually the idea of, because the total harmonic distortion is calculated as a summation of all components. It's not only for this moment. So, but the distribution of the total harmonic distortion somehow modified, stabilized in the system because of the modified version of the algorithm. A comparison for the results. Those are the three results. Version and modified version, voltage and frequency, and the hybrid. As we can see during, this is the efficiency low power, the efficiency high power, as we can see, the efficiency is increasing for where the hybrid method. For the total harmonic distortion, the low power operation was the highest is 12. It goes all the way up to 8, which is like a good improvement for such a change in the system. And of course, those are the frequency results. The same application, I will go fast, but we have figures like this and compare it to the incremental conductance. But we did this something new for the incremental conductance. We checked the system. Those are the, as we can see again, this is the correlated power and the low power for the incremental conductance at the same. So I shouldn't look to the current I say and see like, okay, this current it doesn't, this current contains interharmonics and this one not, because this one looks sinusoidal. No, there is sinusoidal. And the idea, so the reason is not the shape of the current, the reason is something else, which is the DC-link voltage, the perturbation of the DC-link voltage. So this is the modified voltage, incremental conductance. It's somehow similar to the vector number Z, not the same values, but similar. It's also suppressing the harmonics. This is the modified frequency of the incremental conductance. And those are the comparisons. As we can see, this is the efficiency. The efficiency for the high power and the low power. As we can see, the efficiency a little bit different from the vertical unobserved, but the efficiency curves, they are like the same trend. They are, and also the total harmonic distortion.
above 8 and something plus 8 in the vertive and observed. And finally, if we would like to compare the modified vertive and observed and the modified incremental conductance, both the proposed method, as we can see, it's strange. Both of them working in specific areas. So it's like the vertive and observed is shifted from the version of the incremental conductance, as we can see in the results. The red is vertive and observed modified, the black is the incremental conductance modified and proposed. Those are, which one is better, I don't know. For me, for example, maybe you can see here, this is a little bit more than, so maybe we can say vertive and observed better. They are the same for me. Even it's well known that a little bit the incremental conductance is better. But it depends. So for me, I think they have the similar performance. The neural network maximum one checking algorithm train a data, solar irradiance from the MATLAB, taking the data and training the model, then running the system again. It behaves much like the constant voltage maximum one tracking algorithm. Pre-train, one of the main problems, aging, like the inverter is aging, parameters needs to be updated, the neural network needs to be retrained again. So this thing is sometimes exhausting, but it's good because it's with the advancement of the neural network, it's really becoming so easy to update this matrix, this net matrix. The neural network total harmonic distortion is 1.5. The lowest one actually it was the constant voltage with 1.2, the lowest harmonic distortion in the system. Those are the summary of all the methods that we did. Total harmonic distortion, oscillation for the rated power and for the low power. And also those are the thing that we are added to our proposed, which is the level of interharmonics low to medium. But the lowest are the modified random hybrid techniques, using both the sampling rate and the step size. Checking the system, it's only for checking the system performance under dynamic response of the system, changing the solar irradiance 1,800, 600, 1,000. So the system is going fine. The settling time is like 200 milliseconds, I think, over 250. So the system is responding very fast to the steady state. And as we can see, under this situation, as we can see, this is the solar irradiance. We started 1,000, 800, 600, 10,000. The system, as we can see, the current is going down. This is the same. The current is going down until going all the way. This is the active power, the active power, and this is the total harmonic distortion under the proposed method. We added the multi-mission profile, which includes the voltage target group, the cycle swing detection, active power limits in the system, also the Q compensation in the system, frequency deviation analysis, we will check what will happen, and finally we check a very slight thing in the system, which is the DC link capacitance, to check what will happen if we change, because there is a study, a lot of studies they are saying the DC link capacitance will go down after, for example, 3,000 hours it will reduce because of the dielectric material. So we wanted to check what will happen. Here we are investigating the system under low voltage target group, the variability of the system. As we can see, this is the grid synchronization, and this moment we apply the fault here. It's a voltage cell of 0.8, and we apply the code of EON. I modified the code. I was mistaken by some equation today morning. The code is EON code. Any code that there is a lot of policies for reactive power support. There is, for me, I saw yesterday like 12 policies. Every company they have their shape and they have their IQ. Okay. So I don't care, but there is a limit. Like for what is the minimum reactive power that I can support? 0.8 voltage cycle, it corresponds to 270 volts out of 310. The peak is 310, it's 270. So the injected reactive power is 400. As we can see, we use the power limiting policy by the apparent power equation. If I'm working in the rated power, if I have a fault, I have a Q here, but the minimum, the power is minimized for the active power injection to keep the power factor within the limits. And then after for faulty clearance, I'm going out. So this strategy is good strategy, I think. It's optional. Maybe someone could leave the inverter on the rated power, but depends. Of course, the performance, this is the total harmonic distortion. We have the triggers here on the time of triggering the fault. And also, this is the variation, the random variation of the DC under the grid support. We found that the total harmonic distortion, before it was 1.8, the modified version, vertical observed, the enhancement is 1.8. The enhancement it was 26%. So we use this, our best method under the low voltage rated through element, and it was 1.8. Of course, during the low voltage rated through, the grid will be unstable. So there will be a variation. There will be like at point of current coupling, there will be a lot of things coming in and coming out. So maintaining this down 5% of total harmonic distortion is good. So we got here 3.9, which is still within the code, despite the fact that we have a fault. No one is looking for the total harmonic distortion, but it's possible. A comparison between the vertical. If we apply low voltage rated through for the conventional vertical oscillator, we will get the black spikes of interharmonics. During the low voltage rated through, the spectrum is in the red color here, and it's like suppressing all the harmonics that we have. Here is the vertical observed low voltage rated through obtained with the dynamic grid somewhat on another from another section of the current, because during at the transition. This is at the transition. This is the steady state. I mean, this is at the transition, and the good one, let's say, this one during the steady state low voltage rated through. So we can consider this for clarity of the results. Another fault, 800 bar. So it will be the same concept, but we are testing the injected active power to the system. Those are all the results with, let's say, low power and high power. There is something very strange, the behavior of the DC link. As we can see, as the behavior was a little bit with high peaks under the low voltage, which means that a little bit the system is, the inverter is stressed.
It's quite normal.
Yes, of
We are
course.
controlling the active power injection in case of frequency deviation. So you are also controlling the active power by controlling the DC link. So
Oh, okay.
there will be a
Okay.
deviation of DC link voltage also.
Yes.
So it's normal.
So thank you very much. Sure. And this is actually up to some level, doctor. It will be like maybe the inverter will be done. So under this situation, we are checking the frequency sensitivity. Like we change the grid frequency by half hertz, which is 1%. I think it's acceptable in the code to change by half for a specific amount of time before disconnecting the inverter. Up to the code that I read from, 1% is somehow acceptable. So we applied this. On the moment I was watching let's say, the grid voltage, when I changed the frequency, the grid voltages start at one common to be changing a lot. It was like fluctuating at that point. And maybe this is the main reason why the inverter is trying to, because the fluctuation, not a big fluctuation, but it was fluctuating at the point of coupling. And the idea is that we applied, under this case, I think the algorithm didn't do anything in this case. The frequency changing, the frequency, grid frequency variation, it's very rare. find the frequency in the output changing. But because I think the VR controller, it's not the algorithm. The VR controller, of course, even without the algorithm, if there is a variation in the frequency, the VR controller will not work. Even will inject, sometimes it will be out of service because it's tuned on the 50 Hertz. Any variation sometimes within 1 Hertz or 2 Hertz will destroy the current control.
You should adopt the proportional part.
Yes.
You should adjust the active power. You should follow the grid code. There is a curve. They give a proportion between the active power and the frequency deviation. If the system has the inertial response, in case of a frequency deviation, for example, for 1 Hertz, it corresponds to, if you follow the curve, assume that it corresponds to 1 kilowatt.
Yes.
If you reduce the active power rate, you can see that also you should reduce the proportional part, the proportional, then you will see that the system will be fixed.
And fine.
Yes.
It's a good future thing. Maybe it's a good idea. Yes.
So it's like another application for the
Yes.
control structure.
It's actually they thought about this idea for mitigating interharmonics in the literature to use adaptive gain for the VR controller of the DC link. But it's a good idea, but it's a trade-off also with the efficiency. So I don't know.
Because the resonant part is like a modulator. You can tune it to the exact harmonic levels. For
Yes.
example, for 150 Hz, 250 Hz, or 350.
Yes.
So you can increase
No.
the numbers. Yes, it's not for the interharmonics.
I think it's a good idea. I will keep it. I will keep it. But usually, so this is why I'm mentioning this. This is because of the VR controller. So I'm not thinking it's because of the algorithm itself.
Yeah.
So this is a good. Actually, this is a good trend. I left it here as a good trend for the future version. Continuing this thesis. Finally, we are discussing the last one, which is the DC agent. The literature is saying that, for example, 3,000 hours of operation of the capacitance, the ceiling capacitance, will decrease it from 2 to 7%. I took them as average numbers from many papers. They did numerical analysis and tables. So I took 5%. Like I made range, and checked 5%. It's not logical, for example, to check for 15. So it should, based on some calculations. So after 6 months, what will happen, for example? So I checked with 5% variation of the DC length, what will happen with the spectrum of the interharmonics. I was expecting something. This is something very, very small. You can't even notice. So I think with the aging of years, we have to have a model of the inverter expecting the capacitance value after 10 years, for example. So I don't know how much it will be. So, but it's good to know that at least the variation after a specific period of time is indicated in the spectral analysis. As the conclusions, of course, we are confirming that the photovoltaic inverters are a source of interharmonics, since and specifically the maximum power point tracking algorithm and the perturbation. We are also concluding that the strong and the very strong relation between the maximum power point tracking algorithm and the interharmonics distributed through the frequency spectrum. Also, we can say that the parameters that, of course, we have a dominant, I'm just repeating. There is no power dependency between the low power and the high power with the interharmonics. I just stressed this point many times, but there is no power dependency. The dynamic grid support slightly reduce the peaks of interharmonics, the grid support, and also stabilize the grid voltage. So maybe stabilizing the grid voltage is a big reason for also reducing and also increasing the algebraic sum of the power injected to the grid is also reducing somehow the interharmonics up to some limit, not so much because of the power dependency, but it's somehow reducing a little bit. If you saw the number, there was like a very small difference, but not like a huge one. As the paper like we saw before, there was like this difference between the low power and the high power. Of course, we can include a 26% improvement of the proposed hybrid variable algorithm for the vertical observed and the incremental verticals as well. And we also covered the mathematics about the DC link voltage, how the DC link voltage is formed, and the frequency analysis of it. Just to sum all the results out, we have all the methods that we compare together. This one is a contribution to the thesis. This one is contribution, and this one is also contribution. We have like a total of 7 contributed methods in this thesis compared together. Four of them like very novel contributions. So like the incremental conductance, for example, I didn't see incremental conductance. So on those figures comparing the efficiency and the total harmonic distortion, we see that this is the unified value. It's here. For the low power operation, this is when we have efficiencies. The unified random is 969. Actually, the incremental conductance a little bit better than the vertical observed with the efficiency calculation. Those are the total harmonic distortions. It's only the same figures before, but summed together. And also we can notice those are the let's say the offline, not with the. I'm comparing those. Sometimes I'm comparing the constant voltage with the artificial intelligence because they have a similar. There is no perturbation of it, and you will see they are the top actually, but they have their limitations, like specific limitations in the usage of the inverters.
It's neural network, right?
Yes.
Artificial intelligence.
Yes.
Not other.
No, yeah,
Not any other.
no, it's feed-forward network trained with I think two layers, and yeah, it's a regular one. And here we have the summary of the results. Yeah, this is the first basis, efficiency, total harmonic distortion. The research, actually, all the topics I was mentioning them during the presentation, but with this, then we can use the equations of the interharmonics as a detection signature, for example. We can design a neural vector, and we can detect this one using the mathematics. Like, for example, the singular variable decomposition or the eigenvalues. We can generate the number of harmonics based on those equations and feed them as a feature extraction, the feature vector for the neural network. So it will be fine, a good point. Also, the DC capacitor, studying the effect in more details, what is going on with the value of the DC. Check for any possibility. This thesis is actually changing the software. We change the software in a very, let's say, cheap way. It's like it costs you nothing, changing the software, but maybe there is a hardware for the interharmonics. And extend, of course, working more on the mathematical modeling of the system. I would like to thank you all for your attendance, and I acknowledge Dr. Ahmed Tiki for his support during those years. He was so patient with me and supportive during all the steps. And also I would like to thank the committee members, the jury members for joining, and especially Dr. Kuzgur. He was of a big hand. We worked a lot together. And also we collaborated in a lot of meetings along with Dr. Ahmed. It was all the time here and the teams. Thank you very much. And also thanks for Dr. Taimur. Dr. Qasim, actually I saw you before years. It was on, not on a good occasion. It was on Fairmont. Someone here in the department. I remember at that time. And thank you very much, Dr. Musa Murad, for your coming from a long distance. Thank you for my friends for joining us to this presentation. I would like also to give a special thanks to Ad Hakan. He was like a brother during my stay in Alama, not like a colleague, as a brother. Really, thank you very much. And thanks for everyone. I would like also to thank and I would like.
Everyone.
radiation energy reports. It's Q2